11, Law 5 on conservation of energy. So the law of conservation of energy stems from the first law of thermodynamics. It states that energy cannot be created or destroyed, just transformed from one form to another. And energy forms such as potential and kinetic energy are conserved in a closed system, and energy such as friction, which is a form of thermal energy, is lost to surroundings. And the formula for gravitational potential energy is mass times gravity times height. And then the formula for kinetic energy is 1/2 times mass times velocity squared. And oftentimes, like a closed system, gravitational potential energy and kinetic energy are just converted to each other and energy is conserved. So that's why these two formulas are relevant. And the objective of this lab is to explore the conservation of energy using Newton's cradle. So we will explore how the motion would be ideally without any loss due to friction versus a real-life model. Ideally, the x and y distance would oscillate and reach the same amplitude every time because energy would be conserved. And in the real world, however, each collision causes energy to be lost to the surroundings due to sound, friction, thermal energy, etc. Therefore, the balls would eventually stop. But under ideal conditions, the cradle would be able to go on for an infinite amount of time, reaching the same amplitude every time. So here's the video I used to track the motion. And then here's the real data I used. And so this compares the collision number to the amplitude of the ball in degrees. So as you can see, the amplitude decreases over time as collisions increase. And then this is the data from Tracker, which represents the ideal model. So as we can see over the 3 collisions, it reaches the same amplitude every time, and it shows like simple harmonic motion. As we can see, the shape of the graph indicates that energy is being converted between kinetic and potential energy. So the tracker model represents ideal conditions because it only looks at the motion for 3 collisions, and at that point an insignificant amount of energy has been lost. And the data in the first graph represents real conditions because it looks at the motion over 40 collisions, so a significant amount of energy is lost over those collisions to the surroundings. So in the tracker model, conservation of energy can be observed. The ball reaches about the same amplitude after each collision, which can be seen in the graph and in the video. In the beginning, we can see that it reaches about the same height every time. And as we saw in the graph, it reaches the same height every time. And the data in the first graph shows how in the real world, energy is lost to the surroundings in sound, friction, etc. because the amplitude decreases as collisions increase, and it decreases with each collision. As we can see at the end, it's much lower than it was at the beginning. And so here are the references for the video and for the data. Thank you.